The sixth generation disruption. In the United States, sixth-generation combat aviation has shifted from theory to funded programs with defined timelines. The Air Force's next-generation air dominance effort, a deliberate system of systems approach, is now in active development. At its center is a Boeing-led manned fighter, often referred to in defense circles as the F-47, with surrounding families of supporting systems, autonomous drones, advanced sensor networks, and resilient battlefield communications. While program goals include technologies such as adaptive cycle engines for greater range and performance, integrated AI copilots to manage data and coordinate unmanned teammates, and spectrum-wide signature control, these remain targets rather than operational realities. The Navy's parallel F/A Roman 20 program follows the same philosophy, but is purpose-built for carrier use, prioritizing unrefueled reach for operations in the Pacific, flexible payload options, and maritime hardened systems. Both services aim to leap beyond the incremental upgrade model that defined prior generations. The concepts start with stealth as only one layer in a broader survivability package, integrating distributed and passive sensors throughout the airframe and interconnected systems. Networked in real time, these aircraft are envisioned to serve simultaneously as strike platforms, reconnaissance nodes, and battle managers. AI decision aids could reduce pilot cognitive load, enabling manned crews to orchestrate multiple unmanned assets in contested environments without losing situational awareness. Among the most potentially disruptive elements are loyal wingmen drones, autonomous or semi-autonomous aircraft equipped for sensing, jamming, decoy, or strike missions. They would operate in concert with manned fighters, probing defenses or engaging targets while keeping human pilots out of the most dangerous positions. Program objectives call for seamless in-flight retasking of manned-unmanned formations, allowing strike packages to adapt quickly to changing threats. Abroad, allied governments are advancing parallel sixth-generation plans. The Global Combat Air Program, led by the United Kingdom in partnership with Italy and Japan, aims for the mid-2030 with an emphasis on sensor fusion, advanced propulsion studies, and human-machine teaming competitive with US developments. On the continent, the France-Germany-Spain Future Combat Air System targets a similar in-service window, built around a combat cloud, linking a next-generation fighter to drones, satellites, and ground networks. Both mirror the US approach of pairing an advanced crewed platform with autonomous systems under a shared digital battlespace, adding pressure on timelines and reinforcing the shift in force design. China and Russia are also pursuing their own paths toward post-fifth-generation capabilities. Public information is limited, but reporting suggests Chinese research into adaptive propulsion, multi-domain networking, and pilot drone teaming, while Russian work appears more focused on affordability and integrating hypersonic strike into stealth platforms. Even if these efforts trail the US or its closest allies in certain technologies, their existence accelerates the imperative for sixth-gen readiness in Western planning. For Lockheed Martin, the change in procurement landscape carries strategic weight. Despite decades of dominance in the fifth-generation market through the F-35 and its experience with the F-22, it is not the prime contractor for either the Air Force's NGAD manned fighter or the Navy's F/A Roman 20. That means the centerpiece aircraft in each service's future frontline mix will be designed and built without Lockheed in the lead role. The prime-level contractors will set architecture choices, shape sustainment models, and lock in proprietary frameworks that could define air combat for a generation. Lockheed remains engaged in advanced research, holds intellectual property from its NGAD bid, and maintains development capacity in key technologies such as avionics, sensors, and mission systems. According to CEO Jim Takelet's public statements, elements from its NGAD design work can be adapted for use on existing platforms, including the F-35 and even the F-22 where relevant. Yet the absence from prime status in the US manned sixth-generation programs changes its degree of influence. Subsystem supply contracts sustain a technical presence, but they do not offer the same leverage over future upgrade schemes or overarching combat doctrine. For current F-35 operators, the emergence of these new aircraft ecosystems brings practical considerations. Sixth-generation fighters are likely to employ different software environments, logistics networks, and maintenance training regimes. Moving from an F-35-centric fleet to a force anchored by a sixth-gen system could involve parallel supply chains for years, with associated costs and complexity. Each Air Force will have to weigh the potential capability advantage against the disruption and expense of introducing a fundamentally new design. The operational ambitions of sixth-generation concepts go beyond higher speed or stealthier profiles. Adaptive engines aim to shift in flight between efficient cruise and high-thrust combat modes, potentially extending range by a quarter over today's stealth jets. AI support crews promise to filter and act on the torrent of sensor data that would overwhelm a single pilot, particularly in dense electronic warfare conditions. Distributed sensing means a formation can detect, track, and target threats without emitting from its own radar, reducing exposure to adversary detection. Loyal wingmen expand offensive and defensive options without adding more manned cockpits to the order of battle. Combined, these targeted advantages could make it difficult for even upgraded fifth-generation aircraft to match the operational flexibility of clean-sheet sixth-generation designs. Airframes constrained by original assumptions, single crew workload, certain aspect-dependent stealth shaping, fixed propulsion, can integrate new tools, but rarely as deeply or efficiently as a platform conceived with them from inception. This gap is why procurement planners often earmark entirely new designs for leaps in capability, rather than relying exclusively on legacy platform development. For Lockheed Martin, the structural challenge is clear. Their F-35's production line and global sustainment network ensure its presence into mid-century, but leadership in defining the next era belongs to those shaping the first operational sixth-generation fleets. Without a prime role in NGAD or F/A Roman 20, Lockheed must look for other ways to influence and participate in that future battle space. The company's approach, publicly signaled in recent years, has been to reframe its flagship fighter not as a legacy design frozen in time, but as a platform with headroom for major capability growth. Advanced avionics from future programs, next-generation weapon integration, improved thermal management from adaptive engine research, and manned-unmanned teaming concepts could, in theory, be adapted to the F-35's architecture. If those capabilities can be brought to service quickly and affordably, the argument follows that the gap to sixth-generation designs could be narrowed enough to preserve relevance. This is the competitive environment in which new proposals are taking shape. For Lockheed, maintaining its position in the world's most capable air forces now depends on translating its research and design investments into upgrades that matter to current operators, and doing so before the sixth-generation fleets arrive in numbers. Conception of the Super Lightning. Lockheed Martin's Super Lightning concept emerged not from a formal Pentagon program, but from a deliberate internal pivot. The trigger came in early 2025, when CEO Jim Taiclet told investors during the April quarterly call that the company intended to apply technologies developed for its next-generation air dominance and other sixth-generation bids to existing F-35 and F-22 platforms. He set a clear challenge for his engineers: deliver roughly 80% of the capability jump expected from sixth-generation designs, but at around half the cost. It was Lockheed's own strategic pitch, not an endorsement from the US Air Force, aimed at turning stranded research and development into a marketable advantage. The thinking was straightforward. Losing prime contractor status on NGAD and the Navy's F/A Roman 20 had left Lockheed with advanced concepts, prototypes, and subsystem test data that were no longer tied to a funded fighter program. Scrapping that investment outright would mean writing off years of R&D, folding those technologies into the already proven F-35 airframe offered a way to monetize them, while keeping the company in the conversation about cutting-edge combat capability. Inside the company, the Super Lightning idea drew on work already done for clean sheet 6th generation proposals, conceptual designs, wind tunnel evaluations, and component prototypes. These included improved low observable coatings with better durability and multi-band performance, autonomy and AI-driven mission systems for threat assessment and route planning, manned-unmanned teaming frameworks, advanced sensor and data fusion packages with expanded processing throughput, and compatibility provisions for upcoming long-range and multi-mode weapons. While originally conceived for new aircraft architectures, engineering teams assessed that these elements could be adapted to the F-35 with targeted structural modifications and systems integration. The appeal to customers was clear. An F-35 enhanced with this technology suite could be positioned as an evolution, not a replacement. Existing F-35 operators, now numbering in the thousands, had already invested heavily in pilot training, maintenance pipelines, simulator infrastructure, and spare parts stocking. Keeping those investments relevant, while gaining much of the intended operational impact of a 6th-generation fighter, would avoid the cost and disruption of introducing an entirely new airframe. Lockheed's internal projections avoided headline comparisons on raw speed or pristine stealth from every angle. Instead, engineers concentrated on the attributes that most influence combat outcomes in realistic scenarios: reduced detectability by emerging sensor networks, computing power to process and exploit growing volumes of sensor data, expanded engagement envelopes for both air-to-air and strike weapons, and partial automation to help a single pilot manage complex, multi-asset missions. Performance gains of that kind could deliver tangible tactical advantages, even without matching every technical specification of a purpose-built 6th-gen jet. Strategically, the Super Lightning offered answers on several fronts. To long-term F-35 customers, it suggested a route to remain competitive without waiting for the 2030s. For Lockheed, it kept advanced fighter manufacturing and integration skills engaged and profitable. For governments, it provided an option that could be bought in quantity and brought into service sooner, sidestepping some of the cost and schedule risks that come with scaling up an all-new type. Technical transfer candidates from NGAD work were prioritized according to impact and integration cost. Stealth refinements for the rear aspect of the aircraft targeted vulnerabilities against modern, full-sphere radar systems. Mission computers designed for AI-assisted control of unmanned teammates could be swapped into existing avionics bays, enabling advanced coordination functions. Onboard AI copilots, software agents capable of monitoring the battle space, correlating sensor tracks, and recommending courses of action, could be layered into pilot workflows without wholesale redesign of the cockpit. New weapon interfaces could bring in evolved missile types able to engage multiple target classes with adjustable seeker modes. Even defensive technologies, such as compact, directed energy countermeasures, first explored for use on autonomous escorts, were considered for adaptation. From a sales perspective, this hybrid approach played to practical procurement realities. Many Allied air forces were under budget constraints, juggling investment in drones, missile defenses, and cyber capabilities alongside their fighter fleets. Extending the relevance of existing jets at manageable cost was likely to resonate more than committing to an unproven design with a long delivery horizon. There was also a geopolitical logic. Access to US 6th-generation aircraft will not be universal. As with past fighter programs, export versions are expected to carry performance restrictions. A Super Lightning upgrade path could serve as the top-tier exportable option, offering much of the operational benefit without breaching sensitive technology controls. This would reinforce Lockheed's role as a key partner, keeping allied forces aligned with US operational methods and sustainment systems. Timeline pressures reinforce the business case. Operational sixth-generation fighters in the US inventory are not expected in mass numbers until well into the next decade. Adversary capabilities, especially in integrated air defenses and sensor fusion, will continue to advance in the meantime. A fielded Super Lightning variant could narrow the performance gap quickly, complicating any attempt to exploit a window before sixth-gen fleets mature. Lockheed has been candid that this is a trade-off. Even with substantial upgrades, a re-engineered F-35 will not replicate every advantage a new generation fighter can deliver. Airframe shaping constraints, propulsion integration limits, and baseline systems architecture all set boundaries. But the company's public argument is that the capability versus cost balance will still favor this evolutionary approach for many operators until sixth-generation affordability and availability improve. Framed this way, the Super Lightning is less a side project than a deliberate realignment of resources and ambition. It represents an attempt to recast the F-35 not as yesterday's platform, but as a foundation robust enough to absorb key advances from the next era of air combat. The substance of that transformation rests in specific hardware and systems changes now being evaluated, alterations intended to close those most exploitable gaps against future threats, while preserving the strength that made the jet valuable in the first place. From the cockpit outward, these proposals begin with the areas most visible to an adversary's sensors. Proposed airframe and stealth enhancements. Lockheed Martin's plans for the Super Lightning start with physical changes the company claims could reduce the aircraft's detectability across a broader range of viewing angles. One of the headline priorities is lowering its rear aspect radar signature. The baseline F-35 was shaped primarily to defeat frontal and side radar threats typical of the early 2000s, assuming radar sites or interceptors would try to spot it head-on before it launched weapons. Current integrated air defense networks use distributed radar nodes and passive sensors positioned to cover multiple sectors. When a stealth aircraft passes those sites, the heated exhaust area and aft fuselage become far more visible. Lockheed's engineers have identified reshaping aft fuselage edges, tail boom contours, and the surfaces around the nozzle as possible ways to scatter or deflect radar returns in that hemisphere. These remain design studies, not fielded modifications, and company officials acknowledge that rear aspect shaping will be carefully balanced against cost and aerodynamic trade-offs. Infrared signature control is tied closely to that radar work. Modern infrared search and track systems on fighters, ground stations, and even large surface ships can detect an engine heat plume well before visual contact. In the Super Lightning concept, cooling approaches adapted from Lockheed's sixth-generation R&D are under review for the rear section. Ideas include modified nozzle shrouds, ceramic heat shielding designed to spread and cool exhaust flow, and active airflow channels to mix ambient air with hot gases before release. Each is intended to reduce the intensity and concentration of the heat plume during high-thrust phases. If adopted, this would complicate targeting by advanced imaging infrared sensors, though the company notes any such integration would have to pass performance, weight, and maintenance assessments first. The proposal also includes adjustments to existing inlet and outlet designs. The current S-duct inlets block a direct radar line of sight to the compressor face, but testing has shown angles and frequencies where returns still occur. Lockheed studies look at slightly altering inlet lip geometries, incorporating sharper edge treatments, and layering more radar-absorbent material along internal surfaces to further attenuate unwanted reflections. Exhaust nozzle edges could be given serrated or reprofiled contours to scatter radar energy, especially for low-frequency systems looking down the tailpipe. Lockheed frames these as refinements that could be added during production or major overhauls, distinct from wholesale redesigns, which would approach creating a new aircraft with higher cost and schedule risk. Upgrades to radar-absorbent coatings are also part of the package. The F-35's original coatings were optimized for the radar bands most common on threat systems during its design phase. In the past decade, adversary sensors have expanded into both lower frequency surveillance bands and higher frequency targeting sets to bypass so-called frequency-tuned stealth shaping. Lockheed says its newer coating formulations broaden the absorption range into challenging L-band and low OOF spectrums, while also improving resilience to weathering and abrasion. That matters because stealth sustainment is already a known issue. US test and operational reports have flagged the labor-intensive process of repairing and reapplying coatings as a persistent burden. Introducing more complex geometries or advanced materials could improve survivability, but also make upkeep harder, an operational trade-off any customer would need to weigh. Lockheed's emphasis on rear aspect and low-frequency protection reflects changes in the threat environment. Multi-static radar arrays can network dozens of smaller emitters over large areas, pooling their returns to detect aircraft from angles assumed safe in the past. In such conditions, reducing the chance of a successful rear aspect track is more than a niche gain. It becomes necessary for any deep penetration mission. Above and around those networks, high-altitude surveillance aircraft and space-based platforms bring downward-looking radar and infrared systems into play. Here, aft body recontouring, reshaped edges, and diffused exhaust flow could help break up the symmetry of a contrail or heat trail, delaying a positive fix. The company stresses the modular nature of the F-35 design as a facilitator for these changes. Most exterior shape adjustments under consideration do not require rearranging internal fuel or systems, making them compatible with both new builds and major depot visits. Coating upgrades could be applied during routine surface maintenance, and inlet or exhaust changes incorporated into engine servicing cycles. That update path is central to Lockheed's sales argument, closing part of the stealth gap to sixth-generation designs without waiting on a costly clean sheet program. Not all airframe changes under discussion are aimed at detection reduction. Range extension is another operational goal, and some operators are already experimenting with solutions. Israel's work on conformal fuel tanks and external drop tanks for its F-35 aims to provide longer reach in scenarios where low observability is less critical, such as transiting friendly airspace or during egress after weapons release. These modifications illustrate the trade-off inherent in any airframe addition. More fuel extends range, but increases signature, so their use must be tailored to mission type and threat environment. For the Super Lightning, Lockheed could build on such precedents to offer optional range packs that integrate with the proposed shaping and coating changes. Engineering all these enhancements demands careful performance trade-off analysis. Measures that cut infrared output can sometimes add drag or constrict engine airflow, impacting acceleration and range. Lockheed's development studies use computational fluid dynamics to evaluate dozens of aft body and nozzle variations, looking for combinations where signature reduction outweighs performance loss. The company's position is that the right mix can extend the jet's survivability without compromising its multi-mission flexibility. Operationally, improved rear aspect stealth has clear effects in dense threat regions. In the Pacific, where sensor sites can be spread across island chains, an egress route may still take a strike aircraft past hostile coverage. Reducing detectability here could prevent an enemy from vectoring interceptors or tracking the aircraft to vulnerable en route points like a tanker. In European airspace, low-frequency radars and infrared detection grids reach across borders. A higher detection threshold forces an adversary to rely on its most advanced assets or accept gaps in tracking coverage, complicating their response and buying time for friendly forces. In Lockheed's framing, the combined effect of shaping tweaks, exhaust treatments, and expanded band coatings would not transform the F-35 into a sixth-generation jet, but would slow the erosion of its edge. By addressing radar and infrared vulnerabilities from more angles and frequencies, The Super Lightning package is meant to extend the period in which the aircraft can enter defended airspace, complete a mission, and exit without early interception. That survivability interval is the value proposition, keeping the fifth-generation platform viable while the next wave of fighters is still in limited service. These structural and signature management studies form the foundation of the Super Lightning's external upgrades. From here, Lockheed's concept turns inward, examining changes in how the aircraft thinks, senses, and fights, areas where advances in computing and control could shift its role well beyond what its current cockpit and systems were designed to do. AI integration and autonomy.